Started. There is a problem that we have talked about earlier, that when we look at a common source amplifier, the problem that we have is that in the circuits that we have discussed so far, we put a bias voltage here and we put the source, the input source, and we have connected them in series in this particular manner here, right? And I have said that many times the input source has one terminal as ground, and the bias voltage also has one terminal which is ground, right? And therefore, we can't simply connect them in series in this manner. If both of them, one end is ground and one end is ground, then what happens is one of them will get shorted. Okay, so the issue is, how do I connect the input and the bias voltage in series when one of the terminals is ground, which means that I don't have floating sources. In floating sources, both the terminals are available to you and you can connect them in series, there's no issue. But if one of them is ground and the other one is also ground here, right, one terminal is a ground, then you can't simply stack them up. So the issue is, how do I connect them in series? I need to apply, V bias needs to go to the gate and the input also needs to go to the gate, and they need to sum up. How do I do that? What is the solution? Okay. Well, this is a solution that you guys are well familiar with, right? So in other undergraduate elementary courses, you've seen that you use R1 and R2 to generate the bias voltage here. Note that the bias voltage, when you generate, the bias voltage is here, and then you use a capacitor to couple in the input signal here. The problem with this approach is that the moment you use a capacitor, then it can't amplify a DC signal, right? And or it puts a limit on the low frequency signals that you can amplify here. And the capacitors required a very large, which means that I can't implement these capacitors monolithically. On chip, these capacitors are difficult to make. So this solution is not viable then, right? The capacitors, if you recall, the capacitors were usually in microfarads, and we have said that capacitor on chip is typically in picofarad scale, right? And note that the lower cutoff frequency depends on the value of the capacitor. Typically, it would be 1 over 2 pi, the value of this particular capacitor. And if the value of the capacitor is in picofarads, the lower cutoff frequency itself will go into megahertz. So it's not a feasible solution. So the idea is, the conventional solution that you've seen will not work. The capacitor here. Then what do I do? How do I put the two, the source here and the bias voltage in series? How do I do that? Okay. So one has to look for a way to bias without using capacitors here. So I'm pointing out one possibility here. Look at this possibility. I use a negative supply that you see here, and I put an RS, right? So the idea is we were finding it difficult to apply the input as well as the bias from the same side, right? And so what we did was here, we applied input from one side and biasing from the other side. So I don't need to stack them up, right? So this is a solution that we are, let's say, if we tentatively use here. So now I don't need any capacitors, okay? Although it appears to be fine, a little bit of calculation will show you that the moment I put an RS here, without RS, all of you know that the gain is GMRD. With RS, what will happen is it will become GM by 1 plus GMRS here. So the gain will get reduced. The next thing that I'm sure you are thinking, why can't I make GMRS much smaller than 1? Choose your RS in such a manner that GMRS becomes much less than 1. Then everything is solved. Is that? So GMRS is much smaller than 1. Make it, and if it appears everything is solved, the answer is not true. Let's say if I make RS much smaller than 1, all right. GM is 2. Note that GM will be equal to, what have I written? 2 IDSQ by VGSQ minus VT. IDSQ we have written as, if I look at the circuit, IDSQ, this will be 0. This will be minus VGSQ. And so minus VGSQ minus VSS divided by RS will be IDSQ. And so RS and RS cancel here, right? So GM RS is equal to so much. Now, if I make it much, much less than 1, now you can see why it is difficult. Let me show you some typical values. Suppose this is VGSQ is 1.2, VSS is minus 3.3, this is 1.2, this is 0.7. The value that I get is 8.4. If I look at the typical, for example, if you've looked at the amplifiers that we discussed earlier, we were biasing it at around 1.2 volt, right? And the rest then are 1.2, 1.2, 0.7, minus 3.3, and you get a value of 8.4. So it's not easy to get this condition here. GMRS much, much larger than, smaller than 1, it's not possible. And you're getting an 8.4 here, so 8.4 here plus 1, so you're getting a factor of 9 or 10. And so the whole gain is being reduced by a factor of 10, let's say. And so that's a huge drop. So the issue is that, yes, it allows us to bias, but this RS then has a drastic impact on the gain. So then what do we do? I can't apply from this side both of them. I separated the two. I put an RS here. Well, somebody may say, well, put a bypass capacitor. Right? Put a bypass capacitor here. Suppose for the moment, if I put a bypass capacitor, then in small signal, this is still ground, small signal ground, and I recover my gain back, GMRD. But then what did we gain? If I have to put a capacitor, then capacitor also has to be in microfarads. I can't build this capacitor. So should I ignore this solution? I have a capacitor here. And also, what you are saying is here. Look at this one here. GMRS. Put this as 1.2. And then VSS also. Oh, no, VSS we can't keep on changing. Different VSS we can't keep on changing and making it 1.2 and 1.3. That we can't do. Remember, we need swings and all that to a negative supply and positive supply. So we can't alter the negative supply voltage at various points in the circuit. We can't do that. Okay. So the issue is, but now this is where it something interesting comes in. Do you really need a capacitor at this point? Note what the capacitor, of course, is a reactive element, but really, I mean, all that we require is the following. If you look at this, all we require is that under DC, this should be maybe not allow much current to flow. But what we are looking for is, more importantly, what we are looking for is an element whose, for small signal condition, that element should provide a very low resistance path. It should be like a short. That's what we are looking for. An element which will provide us with a low impedance path to the ground, or which will act like a short, right? Now, can you think of any element such that if I connect it here between this and ground, it will give me a low impedance path? Huh? We have seen that if you look into the source, what do you get? You get a low impedance path, right? One by a smaller path here. So this may be 100K, but then you will get a path which is maybe 1 kilo ohm, right? It will not be like a short. It will not be like a capacitor short, but it will at least provide a very low impedance path to the ground. And therefore, I may recover gain to some extent. Okay, so that's the motivation for saying I can't put a capacitor, because capacitors will take up too much area. But I would like to see what the capacitor is doing, and what we see here is provides us with a low impedance path to the ground here. So the idea is, we've already seen that if you look into the source of a transistor, the small signal resistance is small. It's relatively small, and therefore, what if we replace the capacitor here by something of this sort? Okay, that's the motivation here. So let's do that here in the next circuit. Right? Look at the next circuit here. So instead of connecting a capacitor between here and ground, now remember, we needed a capacitor between connected here and ground. That was only under small signal analysis. Even now here, between this node and this will become ground. Right? So I have connected an element between this particular node and ground. Right? So here, how about exploring a solution like this? Now you can see here that this RS here, there would be a current going into RS. This current would bias both this transistor and this transistor. So by choosing RS properly, I can bias both of them in saturation mode. So biasing we'll see a little later on. Small signal, let's see. There's another possibility, of course, is that I look into a PMOS. So I can connect a PMOS also. But that we will ignore for a moment. Let's go forward and look at this first one here. All right, so let's look at this one and see whether to what extent it solves the problem. Okay, so we do an analysis, small signal analysis here. So we connect V in here, RS is ground, and supply becomes a ground, and we have a situation like this. Now resistance looking into the source is 1 by GM. Okay, 1 by GM here. And then the gain of this particular whole thing will become minus GMRD, 1 plus GM, RS parallel 1 by GM. And if RS is much larger than 1 by GM, which most likely is true, then what I will get is GM 1 by GM will give me a factor of 1. So 1 plus 1 is 2. So I get gain which is 0.5 GMRD. So I don't recover gain fully, right? But I instead of getting it divided by a factor of 10, I get a factor of half only. Right, so this does look like a viable solution. I don't need a capacitor. All I do is I use another transistor that you see here, which provides me with the low impedance part to the ground. Right, and that seems like a natural solution here, 0.5 GMRD here. So here is now, if I do this also, I will get the same gain. Isn't it true? All that I did was I added an R here. Because remember, if I go back here, the resistance looking into it is 1 by GM. And it depends on this R also. But what is this R? 1 plus R by R naught. So, as long as this R is not very large, it doesn't really matter. So I can add even an R here. Even an R here. And now something becomes interesting, which we will see in a minute. I get a gain. Normally when I apply input, I get a gain here. But now I will get a gain here also. And now what happens is this. You will see that this voltage is exactly same as this voltage, but they are 180 degree out of phase. So now, instead of defining V0 as between this node and ground, if I define V0 between this node and this node, what will I get? I'll get 0.5 GMRD here. I'll get minus 0.5 GMRD here, and you take the difference and you get GMRD. So I've recovered my entire gain. So in a way, I've solved the problem. I was looking for a way to solve my biasing problem and not sacrifice the gain. So I've biased it also by using this particular transistor, using this particular transistor to provide a low impedance part to the ground. And by defining V0 not between here and ground, by defining V0 between these two nodes. And I've recovered the gain also. So I have GMRD, I have my biasing, everything is fine. And now you begin to see that this is looking like a differential pair, right? Now I can apply an input from this side also. So it becomes a differential pair. So what you are seeing here is differential pair is a natural solution to the biasing problem that I was talking about. That you need to apply a signal also, you need to bias also without using any capacitors. Well, differential pair is the solution to it. Okay. So for example, let's quickly do V01 and V02 here. So we define V0 equal to V01 minus V02. And the resistance, as I said, when you look into it, you get 1 by GM, 1 plus RD by R naught. So it's practically equal to 1 by GM. So V01 is 0.5 GM RD VS here. And same thing for if you want to calculate what is the gain here. Our method is to calculate Norton's current at this particular point. Now note this part here that you see. All this using our method, we can approximate it by GM VS times 1 by GM, which means build Norton's equivalent at this point. When you build Norton's equivalent at this point, the current you will get is GMVS. The Norton's resistance at this point will be 1 by GM. So this part that you see in red is Norton's equivalent is here. Okay, using those 4 sub-circuits that we had given earlier, you can easily show that this is Norton's resistance. Of course, you clearly see is 1 by GM. Norton currents also you get GMVS. So body effect I'm neglecting for a moment. So this whole part becomes GMVS 1 by GM, and then we have RS connected here. And then we have this transistor connected here, right? And so now you see what will be the Norton's current. Norton's current would be this GMVS that you see here. It has a chance of going into 1 by GM or RS or into the transistor M2. Obviously, RS it will avoid, and resistance looking into M2 is also 1 by Gm. So half of this current is going to flow into M2. And once it flows into M2, it will come out of the ground. So IN is going to be minus 0.5 GMRS. Okay. And Norton's resistance at this point is simply RD. All right. So that's why Rn equal to RD. That's why we get a gain which is 0.5 GM RDVS at this point here. So the voltage at this point is exactly same as this point, 180 degree out of phase. Okay, so that's what we are finding. 0.5 GM RDVS here, and it was minus 0.5 GM RD here. So V0, if you define V01 minus V02, you get minus GM RDVS. Right? So you recover your entire gain. Now, of course, you may say, well, now my voltages are floating. Both ends are floating. Normally, you may want a voltage between a node and a ground. Okay, so that problem is still there, but we'll see how to tackle that again. So, as a solution to the biasing problem, we have arrived at a differential pair. But differential pair, of course, as all of you know, is useful for other reasons as well. Okay, and the other reason is, that differential pair is an amplifier which is sensitive to the difference of the two input voltages and is insensitive to the whatever is common between them, right? So that all of you know. There are two kinds of differential amplifiers I've drawn here. One is a input, of course, has to be differential, otherwise it won't be called a differential amplifier. Output could be single-ended, or output could be differential in nature also. So V01 and V02 could be differential or could be single. We'll concentrate here on this single-ended output here. Now, a couple of definitions I'll run through, which all of you are familiar with. Differential input voltage is defined as the difference of the two, V in 1 minus V in 2. Common mode is defined as the average of the two. And output we write here as made up of two parts. One is a differential part. So there's a differential mode gain times VID, and there's a common mode gain times VIC here. So output we write as due to differential signal and contribution from common mode signal here. And so we get differential mode gain and we get common mode gain here. And you know that it's a differential amplifier. So what you are interested in is getting AD, which is much, much larger than ACM. And we have a parameter called common mode rejection ratio, which is the ratio of the two, AD by AC, right? Okay, so all this you already know. So this is nothing but just a very simple example here. VI1 is given, VI2, AD, ACM is given here. So you calculate what is VID, you calculate what is VIC here, multiply them together. And so the thing to keep in mind is whatever is common is rejected. The common mode was, how much was the common mode voltage? 1 volt. It got rejected. All that you got was 10 millivolt. And whatever was the difference, which was 10 millivolt, got amplified to 1 volt here. So that's the nature of a differential amplifier that we are thinking of. Okay. Applications you're familiar with, so let me not bother. So let's come to our differential amplifier then. So this is our simplest differential amplifier, M1, M2, biased through RSS here, resistance, and the outputs are available here, V01 and V02 here. I've not shown the inputs because I'm doing a bias point analysis. Inputs, as all of you know, are here at this particular point. Okay, so bias point analysis. We note, first of all, the circuit is symmetrical. Now, in all of these differential amplifiers, unless stated otherwise, we'll assume that M1 and M2 are identical. Okay, so the circuit then is symmetrical, and whatever current ISS is flowing, half will divide here, half will divide here. So we know that. We also know then ISS that you see here, this is 0. So the voltage at this node is minus VGSQ, and this is VSS. So we know that we can write ISS as follows here. VGSQ we know is VTN square root 2 IDSQ by beta, and therefore you have an equation. And if you want to do more accurate calculation, then you have to take into account body effect, because body is connected to VSS here, and therefore threshold voltages will be different. But then through these equations, the analysis is a little bit complicated because of the square root here and the fact that threshold voltage is varying. But conceptually it's simple. One can determine what the different currents are, what the current here, what the bias voltages are. Okay, so it's just a question of these 3-4 equations that are there here. Let me show you an example. We have RD equal to 100K, 100K here. A very simple example, everything is 100K. ISS, after going through those equations, ISS comes out to be 19.23. IDS1 is 9.6 microamperes here. Note, what I wanted to emphasize was the normal threshold voltage is 0.7 and the threshold voltage becomes 1.23. So when you are taking NMOS amplifiers, body effect becomes important to consider. Otherwise, the values that you get for VGSQ and others are not correct. Okay, so body effect. The advantage of PMOS is body is shorted to source, so the analysis is relatively simple in PMOS here. Okay. The other thing about, so that's a rather straightforward bias point analysis. The other thing about differential amplifier that is interesting is current switching. The idea here is that this current that you see, we just calculated the current of 19.23. 19.23 is current here. And when you don't apply anything here and anything here, we know that it goes equally in both M1 and M2. Now, if by applying V in, what we are doing is ISS practically remains constant. It does change because note that as I change the voltage here, the voltage at this node will change, and therefore the current also will change. But as a first order approximation, one can say ISS remains roughly the same. Okay, and what happens is as you apply V in, if V in is positive, what happens is more of ISS flows in M1 and less in M2, right? And if you apply more and more of V in, increasingly more and more of ISS starts flowing through M1. If you go to sufficiently high V in, the entire ISS will go to M1. So current has switched entirely to M1 and nothing will flow through M2, right? And the other thing then that you can do is, this was when V in is positive. If you make V in negative, you can make this current increasingly go to M2. And then by making V in sufficiently negative, you can make entire ISS go to M2 here. So the idea is that this current that you see here in the tail of the differential pair can be switched back and forth between M1 and M2. I can have different fractions of current flowing in M1 and M2 by applying voltages here. Same thing here, because the circuit is symmetrical, I can do the same thing with the voltage applied here. So this is what I mean by current switching. I can switch the current between these two, M1 and M2 here. So that's another basic property of a differential pair here. So as I increase, that's what I said, this voltage increases. So why is it switching? You can see here, as you increase this voltage will increase. And then what happens is the increase here is not the same as increase here. Okay, so for example, let's say if I put 5 millivolt here, what would happen is maybe this is typically 2.5. Okay, so the net increase here is, you increase this by 5 millivolt, this increases by 2.5 millivolt, the net increases by 2.5 millivolt. So 2.5 millivolt will increase the current by a certain amount, but the voltage across this decreases by 2.5 millivolt. So that current also goes down by the same amount, and therefore the two currents add up to be the same. Okay, so that's how the current switching occurs here. Okay, so you can see it in this particular result here. This is IDM1, current in M1, and this is the other one is IDM2, the current in M2. And you can see this is a well-known graph of a differential pair. You can see what happens as you change the value here of V in. So this is at 0, both are equal. Then as you go up, the current increasingly switching to M1 here, and eventually almost everything flows into M1 and nothing flows in M2 here. And the same thing, the circuit is symmetrical, it happens on the other side also. Note that I don't need to apply very large voltage. You can see here almost complete current switching occurs if I apply 200 millivolts. Okay, it's for that reason I was saying that this current ISS does not change that much, because on the other side is minus 3.3, and on this side the voltage can only change by about 200 millivolts, right? So 200 millivolts, and this is 3.3 here. That's why ISS doesn't change too much here. So you can almost think of as a constant current here switching between M1 and M2. Okay, and if the current switches, then you see similar behavior in output also. So as more and more current goes into M1, what happens to V01? It falls. So you can see here the red one, the current is increasing, and what happens is the red indicates V01 here, the output is falling here. Okay, and the same thing then happens on the other side here. So V01 and V02 follow the behavior in M1 and M2. Okay. All right, so that's DC and a little bit about large signal analysis. Let's look at small signal here. Now, small signal means I'm applying VI1 and VI2. And now in differential amplifier, although I can obtain V01 directly in terms of VI1 and VI2, and same with V02, what we do here typically is we define two new signals from the input signals that you see here. We define a differential input signal, which is VI1 minus VI2, and we define a common mode signal, which is VI1 plus VI2 divided by 2. All right. And what we do then, using this differential signal and the common mode signal, in these two terms, we write what is VI1. So VI1 can be written as you can see, VID by 2 plus VIC, and VI2 can be written as minus VID2 by VIC. So the whole circuit can be redrawn with inputs written in this manner. VID by 2 and VIC here, and minus VID by 2 and VIC here. Right? So inputs have been, is the same thing, but rewritten in a different way. And now, because we are doing small signal analysis, what we do is, we do two analysis. One is the differential analysis, where we are going to keep VID by 2 and minus VID by 2 here. And another is common mode analysis, where we are going to keep VIC here and VIC here. So, small signal analysis is broken into two parts, differential mode analysis and common mode. And because it's a linear circuit, any voltage will have a differential part and a common mode part. And I can add them up together to get the net voltage at any point. Okay. So we are going to do a differential and we are going to do a small signal analysis. I mean, common mode here. So differential mode is here and common mode is here. And remember, any voltage, any current, anything in the circuit will have two components here. Differential mode and a common mode. And just add them together. In fact, now note that any voltage in your circuit has three components. A DC or a bias point plus a differential part and plus a common mode part. So it has three distinct components here. Okay. Please keep in mind, don't use the word DC here, because this voltage also can be a DC. Alright. So use the phrase bias point. So at any node that I'm interested in, I have a bias point voltage, and then I have a differential voltage, and I have a common mode voltage. Because each one of them can be a DC also. There's no restriction now. The signal can be a DC also. Differential mode and a common mode can be a DC signal also. Okay. So keep that in mind. Okay. Differential mode analysis. I'm going over quickly because all of you have probably seen something like this earlier also. Okay. So VID by 2 minus VID by 2. This is ground. This is ground. And what do we do next? Yes, you're right. What we do here is we see, because of the symmetry, this voltage will try to make it positive. This voltage will try to make it negative. Both are equal. So it's going to be 0 here, right? So this is, but please keep in mind, small signal ground. It's only under small signal condition that this is ground. There's not a real ground. Okay, so this is all small signal analysis. So this is a small signal ground here. So my circuit simplifies into two halves. Each half looks like a common source amplifier. So look, differential amplifier is nothing but a common source amplifier. Each half looks like that, and we know its analysis here. V01 by VID by 2 is minus GMRD. V02 by so V01, same thing. V02 by minus VID by 2 is also minus GMRD. So we get this two equations here. This is minus 0.5 GMRD. This is plus 0.5 GMRD here. Okay, so that's so this is nothing but the differential gain. One way of defining differential gain is what is V01 divided by VID. So that's differential gain is 0.5 GMRD. Common mode, same voltages on both sides. What do we do now? We also split, right? Common mode. How do we split? 2 RSS. Okay, so we do this. We take RSS here to make it symmetrical. We split it into two resistors, 2 RSS here, 2 RSS here, and we connect it by a wire here. And we note that there's no reason any current should flow here because of symmetry. No current flows into this wire. No current means open circuit. All right, so we open it here. We break it. We get two halves. And therefore, then now I have a simple circuit, and I'm just going to write down the result. V01 by VIC or V02 by VIC is going to be GMRD 1 plus 2 GM RSS here, 2 RSS inters here. Okay, so that's my common mode gain. All right. So ADM we have 0.5 GMRD, ACM we have GMRD 1 plus 2 GM RSS here. Take the ratio and you get the CMRR, which is 0.5 plus GM RSS. Okay. So that's the common mode rejection ratio. How do I make common mode rejection ratio large? Making RSS large, right? So can I get 1000 GM CMRR here? Yes or no? No? Why? Make RSS as large as you want. 1 mega ohm, 10 mega ohm, 100 mega ohm. What will happen? But as you note that you make RSS large, then the current becomes small, GM becomes small here, right? So there obviously is not as simple as simply raise the value of RSS here. So what one can do is one can write what is GM. GM is 2IDSQ by VGSQ minus VT. Okay, and this is RSS here. All right, so let's put them together and note that 2IDSQ is nothing but ISS. So ISS RSS here and VGSQ minus VT here. All right, so now we can write ISS times RS here. The drop here is nothing but minus VGSQ minus VSS here. So we have this CMRR. Now let's put in some typical values here. The values that we had was, so note that it actually very interestingly doesn't depend on RSS. I was saying, can you make 1 mega ohm, 10 mega ohm and all that? You find CMRR is actually independent. It cancelled out because GM also depends on the current. So it cancelled out. It's independent of RSS. Make any value of RSS, it doesn't matter here. All right. First order approximation. Actually, it does depend on RSS. How? First order, you don't see RSS, but what happens is as you change RSS, the current changes, and as you change current, the VGSQ changes here. So first order, it doesn't depend, but of course VGSQ changes here. But what you find here is all that you get is about 11.8512 CMRR. You can't do anything, what can you do? All that, if you look at it here, VGSQ minus VT. So what you'll try to do is make VGSQ close to VT, right? And how will you do that? How will you get VGSQ close to VT? Let's say you decide to bias it at some current, 10 microamperes or 20 microamperes or whatever. So you'll make the size large. As you make the size large, VGSQ will come closer to VT. And so this term will start going up and you will increase. But you will find that CMRR, you can't do too much in this case. There's only very limited space that you have for improving CMRR. And in general, CMRR is very poor of a circuit like this. Okay. The other thing that you see is having a large supply voltage will also help you. Here it is 3.3. If I'm working with 1.8 volts or 1.5 volts, my CMRR is going to be maybe even smaller. Okay. Supply voltage becomes even smaller here. So the idea, I'm sure all of you are seeing where it is leading to. The idea is that I want to have a high value of CMRR. So what do? I replace this by RSS is not a good way of biasing. I replace it by a current source. Okay, so that current source will have very large value of a small signal resistance, and therefore it will have a high CMRR here. So CMRR is low, and so we focus on RSS. We want to make RSS large, but only note that in CMRR we need a large small signal resistance here. All right, so we replace it by a current source, and then of course if it's an ideal current source you get infinity, but that's not true. You will have to use a transistor as a current source, and then the resistance from here to here is R0, and then you know that this will become GM1 times R03. So now you get a respectable CMRR. But GM-R0 you can typically take maybe 70, 80 or 100 or so. So that's all you're able to get even here. And you note that CMRR people want even higher values. Okay, they want 10 to the power 4, 80 dB or 100 dBs, 10 to the power 5. So a single transistor will not help us that much. It has increased GM1R, but not that much. Now, remember what CMRR depends on is the current, is the resistance looking down. So how do I increase the resistance looking down then? All of you know now that you stack it here. And now when you stack a transistor, resistance looking down, you will see now you can easily verify it will become this much. All right. And now you can get a large value of CMRR. So typically if you want to go to large CMRR, you will have to replace the resistor by a transistor, and one transistor may not be enough, and you'll have to stack at least 2 transistors. Okay. Now when you stack more transistors, do you lose something in the process? Swing is here. It's not the swing that you lose. You lose something else. Okay, which we will see in a minute. Okay, so CMRR, that's the route to go for improving CMRR. Okay, so basically you have to make a good biasing source with high output resistance. All right. Okay. Next thing is note that we saw that the differential gain was GMRD, and GMRD if you do, then you know that differential gain is small. To build up large gain, I need to build large resistance, which again is a problem. So our natural solution then would be replace it by an active load. Why use RD? So the idea is use this one. We know that PMOS load here, right? And of course, you may be thinking now one PMOS may not be enough. Stack one more PMOSs, right? So it's the same thing that is happening here. But the trouble that comes here is the following. When I put an active load, I've also shown you that the biasing becomes very sensitive to the voltage here, right? Extremely sensitive here. Further, now you are seeing I need to have some kind of a bias circuitry. So far, I've not talked about at various places I'm putting V bias 1, V bias 2, V bias 3. Where are they going to come from? I have to make some circuit for generating. So I have to make a circuit here also. So there are two issues with it. One is I have to make a circuit for generating V bias. And the other one is this whole circuit is very sensitive. Okay. The whole circuit is very sensitive to the voltage that I apply here. Okay. Now, so that's where the interesting thing comes in. I can have a very small variation, which is here. Same thing that you saw here. The motivation is the same. Use an active load. But now I don't want to use a separate bias circuitry. And I want the bias to be stable. Not to be very sensitive. All that this person did was took it from here and connected it here. In analog circuits, you will see it's just a question of a wire. One single wire, right? You take a wire and you connect it here. That's all. And you'll see the implications of it. What do you think is the difference between the two?
The distance becomes 1 by G.
No, that's there. The distance becomes 1 by Gm. Then how will you build gain? What are the differences that you can imagine now? One wire will make. Of course, I don't need a bias source now. No bias source is required. Now, bias becomes extremely stable. Bias becomes extremely stable. Can everybody see? See, I have this current ISS. This is stable. Agreed? This current is now going to divide between these two. And it will flow here. Now, remember, in one of the earlier homework problems, we've already seen that if I look at biasing, let's go forward and see that. Okay. So let's do the biasing here. All right. So by the way, you can make it using NMOS differential pair with PMOS current mirror load, or you can make a PMOS differential pair with NMOS current mirror load. Both are identical. Okay. So let's come back to bias point here. Now, bias point the issue here is I want to illustrate that bias point is very stable now. Okay. So ISS is equal to will depend on V bias minus VSS VT0 square. Fine. All right. Okay. The 2 is going to divide between these two. Now, there is an assumption here. It will divide equally amongst the two only if V01 is equal to V02. If the two are not equal, in general, I cannot say that. For the moment, let's say the two are equal. V01 then at this point will be equal to VDD minus the source gate voltage drop. And source gate voltage drop is nothing but VTP minus ISS by beta. Okay. So note that if you define this current properly, ISS, which is set through V bias, there's no issue of defining this current properly. Once you define this current, your output voltage gets properly defined. There's no sensitivity, nothing here. Right? You see here, there's nothing which is very sensitive here. Output is precisely defined. And we have already shown you, we'll go over it once more, that this voltage is exactly same as this voltage here. The two voltages are the same. So my bias point now is very precisely defined and is very stable. There's nothing which causes it, the instability that my previous circuit had. Previous circuit had small changes here will cause a large change in V0 here. That no longer occurs. And I don't need a separate voltage here. Okay. So, we have gone through this argument as you know, in order to show that V01 is same as V02. Now I'm doing it slightly more general by saying these need not be ground. All that I require is that the voltage applied here and the voltage applied here are the same. As long as the two voltages are the same, V01 is always equal to V02. Whether this voltage is DC, AC or whatever it is, it doesn't really matter. All that I require is that the two voltages be the same. That's it. Okay. So the argument was assume V01 is greater than V02. Focus on the upper half. If V01 is greater than V02, it implies that the source to drain voltage of this transistor is smaller than this transistor. Right? It implies this. Because the two transistors are identical, they have the same gate to source voltage. It implies that the current in this one is smaller than the current in this one. All right. Next, you switch your attention to the lower two transistors. V01 greater than V02 implies that the source to drain to source voltage of this transistor is larger than this, right? So it implies this one here, and therefore it implies that this current is larger than this current here, and you end up in contradiction here, right? Contradiction, which means that V01 cannot be greater than V02, and you start with V02 larger than V01. Same thing occurs here. The only possibility that you get is V01 equal to V02. Okay, so this result then, what it says is, as long as the two voltages are the same, V01 is exactly equal to V02, right? So the idea is then I have a very stable bias point. All that one did was connected the wire here, and one gets a very stable bias point. One doesn't need a bias circuitry. All our problems are solved. Or is it? As somebody raised a point, I've connected it here, and maybe the resistance here is 1 by GM. All right, but now note, the circuit is no longer symmetrical. I don't have the same voltage here and the same voltage here. Because when I apply an input, remember when I apply a differential input, the voltage here and the voltage here are different. Now, of course, V01 is not going to be equal to V02. Okay, so things will get more interesting now. Now, before I do differential mode analysis, common mode analysis is very simple. Because we have already we have done common mode, because we said the voltage here and the voltage here are the same. Now, look at the way we'll do common mode analysis here. Voltage here and here are the same. So this voltage is going to be same as this. We've already said that. Okay. This voltage is going to be the same as this. Now, don't worry about M3 and M4. Focus on the lower half here. Focus on the lower half. This is replaced by 2R05. R05 I've done again, broken it into two parts. Okay. Again now, because note, again, you see these two transistors as different, but don't focus on that. Just focus on the lower half. You see that this is equal to this. The two transistors are identical. The two voltages are identical. It means what? The current in this wire is again 0. And therefore, again, I can break it up. Again, I can break this up. Okay. And so I break it up. All right. Now, although, now note here, I've written V01 and V0. In a differential pair with current mirror load, my output is going to be actually here. The two, I'm actually going to take the output here. I'm just temporarily writing it as V01, but this is not a useful output. I'm going to take the output here. All right. So when I want to calculate common mode gain, I'm really looking for V0 by VIC. But what have I said? V0 is same as V01. So if I can calculate V01, is going to be same as V0. All right. So now I'm going to focus on this V01, and note that the circuit for V01 is only this. Are you seeing? Because the other part wherever is connected to the gate, it doesn't bother me. Right? It doesn't bother me. On the other hand, if you directly attempt to calculate V0, what will happen is, if you directly attempt to calculate V0, you will have VIC plus this, plus you'll have to worry about this half also, because this half is going to generate a voltage here. So it will become more complicated. So you don't directly calculate V0 by VIC through the right half. What you try to do is you calculate V01 by VIC using the left half of the circuit. And you keep in mind that V01 is going to be same as V0. So don't use the right half part here. That makes the analysis complicated. All right. So the left half of the circuit then is simply here. And this we recognize it as 1 by GM. Okay. And this is 2R05. So we can very easily write down what the gain of this one is, except that instead of RD, we have 1 over GM3. Note that 1 over GM3, and the rest is GM1 by 1 plus GM1 2R05. Okay. Now, something very interesting you will see now. The common mode gain of this particular circuit then is given here. GM1 by 1 plus GM1 2R05, that's coming from here. And the load of this one is 1 by GM3. Do the analysis for this one. Suppose I had not used this particular wire, and I had a bias here. What do you think you would have obtained? This would have been R0. Are you seeing the difference between the two? What one particular wire is doing? How much is the common mode gain here as compared to here? Much smaller, right? The load for this one is 1 by GM, and the load here is R0. So this common mode gain is smaller than this common mode gain by a factor of almost 100. So now you're seeing the advantages that you're getting. The advantages are our biasing became so simple. The biasing became very stable. And common mode gain is maybe a factor of 100 or so smaller than this common mode gain. All right. The benefits don't stop here. The benefits are further. One wire is making a lot of difference. You will find, we'll just show you the gain of this particular one, V0 by VID, is double the gain of this one. So you get double the gain. You get, so compare these two. You get double the gain. You get 100 times smaller common mode rejection ratio. You don't require a separate biasing circuitry, and you have bias voltage, which is very, very stable. All the benefits you get, and that's why nobody really uses this one, and everybody uses this particular current mirror load here. Okay, and I think somewhere, sometime back, people had done a survey of top analog circuits of all times, and this differential pair with the current mirror load is one of those circuits here. It's considered as a top, one of the most widely used and very, very important building block. Yeah. Okay. But now you'll see a lot of interesting things here. Differential mode analysis here. All right. This is complicated. All right. First, I'll do an easy analysis. Easy, but which is a wrong analysis. Okay. I'll do that first. Now, the easy analysis is as follows. In many times, in many of the books, you would find. Now, you remember the past. The past was we were considering M1 and M2 with a resistive load here and a resistive load here. And what did we arrive at in differential? That this point is ground, right? So when people come to differential pair with a current mirror load, many times what they say is, well, this point is ground. But remember, how did you arrive at that particular point? That this point should be ground? You were using symmetry, that the two sides are symmetrical. The two sides are not symmetrical anymore. This side is connected in with gate and drain shorted. This side is not connected. It's no longer symmetrical. So the issue is, can I say this or not? I'll come back to that, but I'll do first a very quick traditional analysis here. So, like in a resistive load, we assume that this is ground. Okay? All right. If this is ground, then the current here, note, the current here, I1, is going to be GM VID by 2. All right, everybody sees that? Current here, drain to source current, is equal to GM VID by 2. The current here is minus GM VID by 2 here, I2. Okay. Now, what happens is next, I1 is equal to I1, note that this is a current mirror. It's a current mirror. Even if you don't know current mirror, look at M3 and M4. They're identical. Their gate to source voltage is the same. So the idea is that I1 will be equal to I4. So the same current flows here also, down. And this is I2 minus GM VID by 2. So what is this current I0? So the idea is I0 is equal to the difference, which is GM VID. Okay, so the net current which flows into whatever load is I0, which is GM VID. All right. Next is, what is the net output resistance? Now you may be wondering, where does it flow? Well, it flows into the output resistance. Okay, it flows into the output resistance of the whole circuit here. So now the idea is, what is R0? Again, put it to ground. And then the idea is, well, R0 is looking from here. So looking down is going to be looking down. So here also, why have I put it to ground? I put it to ground because this is ground, this is ground, there's no current here. There's no current here, right, in this branch. So this point also will be ground. So we put it to ground here. So current, so this will be resistance looking down is R02. Resistance looking up is R04. You're looking into the drain. And so the net resistance is R02 parallel R04. And therefore now my net output current was GM VID. And my current is going to be I0 times R0. And is going to be GM R02 parallel R04. That's what we'll end up. The output voltage is equal to so much. Okay? Because note, I've assumed it to be ground, and therefore there's no voltage here, no voltage here, so this point has to be ground. All right? So then it's, transistor with this ground is R04 and this is R02, and therefore is fine. R0 equal to R02 parallel R04, and you get a gain which is GM R02 parallel R04. Okay? Back, okay? Yes. GMVID by 2, we are saying that we have a transistor whose source is grounded and drain is also connected to almost like a ground to a very low resistance here, and therefore the current I1 is going to be GM times 0.5 VID. You know, transistor model is basically GM times VID. We're ignoring the effects of R0 here. And same thing we are saying here, and GM, except that is going to be minus GM VID by here. I1 is equal to I4, and I4 and I2 together give rise to a net current I0. Okay. Now, while doing the analysis, it's not clear where is this I0 flowing, but I0 is going into the R0 here, the net output resistance at this particular node here. Okay. Now, so this is a very quick, simple analysis which tells us that the gain is GM R02 parallel R04. The final result is correct. Okay. Now, let's do a more slightly more involved analysis here. I've put here 5 millivolt and minus 5 millivolt. Okay. And this is our differential pair with current mirror load M3 and M4. Now, remember what our assumption was? That this one is ground. All right. Is it ground? Well, I went and did the simulation. You can do the simulation yourself. The voltage here comes out to be plus 2.4 millivolt. Okay. This is 5. This is minus 5. You take the circuit and this turns out to be 2.4 millivolt. Obviously, it is not ground. This point is not ground here. So I can't make the assumption, general assumption in this circuit that this is ground here. This is going to create too much of an error. Right? This voltage comes out to be minus 6.15 millivolt, and this voltage comes out to be 0.49 volt. Obviously, because here is a diode connected transistor here, resistance is very small, and here the resistance is pretty large here. So the two voltages are very different. Okay, it's not a symmetrical circuit. If it were symmetrical, then I would have gotten here a 0. It's no longer symmetrical, and you can see the consequences of the fact that it's not symmetrical. This is no longer 2.4. Even though exactly plus 5 millivolt, exactly minus 5 millivolt, all transistors are identical, but the voltage is not equal to 0. This is not small signal ground. The voltage is not 0. This is 2.4 millivolt here. Okay, so that's not true. Then what about the assumption that we were making? Put it to ground and we were calculating all of that. Well, if I don't do that, but you know, our method for calculating gain is what we said, calculate Norton's current. Now, when I calculate Norton's current, what will I do? I put it to ground. Now what will happen? Can you see what will happen? Why was it 2.4 millivolt? Because it was not symmetrical. This was 6.15 millivolt. This one was 0.49. Now what did I do? I made it to ground. Once I make it to ground, this voltage becomes very close to 6.15. So now once you do that, now the circuit is very close to being symmetrical. Very close to being symmetrical for calculating Norton's current. Why? Because this is ground here and this point is also connected to ground through a very low impedance path. So this voltage is almost very close to 0 here. Now what I get is plus 5 and minus 5. Same thing. If I repeat, the voltage here comes out to be 0.059 millivolt. Okay, minus 0.0. It's not perfectly 0, obviously, because the two sides are still not completely symmetrical. But note that this voltage is much smaller than this voltage. So for all practical purposes, I can say this is basically, I can neglect this voltage in comparison to this voltage. Okay, so for calculation of Norton's current, then I can assume it. Now note, the statement that I'm making is for estimation of Norton's current only, not in general. In general, this voltage is not 0 here. Only for estimation of Norton's current, I can assume it to be ground. Okay, so I assume it to be ground, and then of course, as you assume it to be ground, you have a current here and you have a current here. The two currents are there, and this current will go here and will get mirrored here, and this current will be here, and together they will flow up. And IN, I will get something. Okay, so I will use it to calculate IN. So for Norton's current calculation, I can assume it to be ground. All right, let's come to output resistance. Output resistance you estimate by, if you had a circuit, you would apply a voltage and you will see how much current is flowing. Okay, so let's do that. Suppose I apply a small voltage, 5 millivolt. Now, remember in output resistance calculation, what was I doing initially in the simple approach? I was saying this is ground. All right. Now, once I apply 5 millivolt, I get 24.8 microvolt. What should I do? Is it ground? What should I do to 24.8 microvolt? Here is 5 millivolt I'm applying. This is 24.8 microvolt. What should I do? Assume it to be ground? Yes or no? Especially, let me bias you. 0.059 is how much? 59 microvolt, right? 59 microvolt, I assumed it to be ground. Now I have 24.8 microvolt. Should I assume it to be ground? Obviously not, because then it doesn't make, the story doesn't continue. It can't be 24.8 microvolt, can't be ground. Let me show you how. This is 59.6 microvolt. All right, so no problem. GM for this one, you'll see why. GM for this transistors R, for the biasing, is 100 microamperes per volt. R0 is 10 to the power 6, okay? All right, now note, some things, this is why it's important. Something may make sense, some assumption may make sense somewhere. It may not make sense somewhere else. It depends on where you're doing the assumption here. Now, let's start looking at this point here. This is 24.8 microvolt. All right. What is the current flowing here? Let's look at it. Because note that the output resistance will depend on the currents, right? How much current do you think flows here? I2. If you assume that the source of M2 is 0, neglect it. The current that flows here will be 5 millivolt divided by R0. Agreed? 5 nanoamperes. 5 nanoamperes, okay? However, if I actually go and measure, what I see here, current measure, is 2.5 nanoamperes. If I actually go and see how much current is really flowing, it's 2.5 nanoamperes. What does it imply? It implies this is not negligible. The only assumption that I've made is, I said 24.8 microvolt, make it 0. And if I make it 0, then I should get a current of 5 nanoamperes. What actually flows here is 2.5 nanoamperes. What happens is, you can see the current that should actually flow, if I didn't neglect, would be equal to minus GM VGS. Why minus? Because the gate to source voltage is negative. Minus GM, note minus GM 24.8 microvolt plus 5 millivolt divided by R0. It comes out to be exactly 2.5 nanoamperes. What does it tell us? That this current that you see here is not negligible. You have to take that into account. 24.8 microvolts, you cannot neglect. If you neglect it, then instead of 5 nanoampere current down, you get only 2.5 nanoamperes. It makes a 100% error. Then how could I neglect this one? How could I neglect this one? How could I say that this is ground 59 microvolt? I'm saying 59 microvolt here, I can consider it to be ground. While a 24.8 microvolt, I cannot consider it to be ground. Why? Because again, you remember what you are comparing with. 24.8 gate is short. So this one, note that this is GM times this, and you're comparing it with this. There, go back here. 24.8, what is the net VGS? 5 minus this voltage here. Right? 5 minus this voltage here. And this voltage is 80 times less than this. What difference will it make to the current? Nothing. So you are comparing this voltage now with this voltage here. And it's okay to compare and say it is 0. You're comparing this with this one here. While in that case, you're not comparing here. I mean, you have some voltage here. It gives rise to VGS. You're comparing the two currents. The two currents here. This current versus this current here. And here, 24.8 microvolts makes a lot of difference. The two currents are the same. While here, there, you were comparing this voltage with this voltage here. Okay, so that assumption made sense there. It doesn't make sense here. You can't assume it to be 0 here. So now, remember what I was doing for output resistance calculation? I was saying earlier that assume it to be 0. Go back and see our simplistic output resistance calculation. What did we do? We said put it to 0, ground. And then the resistance looking down and resistance looking up, and we said R02 parallel R04. And now I'm telling you that I can't do that, right? If I assume it to be 0, then the current which is here is 5 nanoamperes. But actual current is 2.5 nanoamperes. If the current is changing so much, then obviously the resistance looking down is changing so much. So how can I do that? How could I make this point as ground? It's not really correct. Okay. So when you're looking at output resistance, it's not very simple. You can't say resistance looking down is simply the resistance of M2, which is R02. It's not as simple as that. You have to do a more involved calculation. But what happens is, after doing all of that involved calculation, the final result will come out to be R02 parallel R04. Final result comes out to be the same. Okay. So let's do the involved calculation once. After that, we won't do it again. Okay. All right. So before that, let's do the differential mode analysis quickly. So we set IN here, Norton's current. In that case, we said we can assume it to be ground. For Norton's current, we can assume it to be ground. All right, ground here and ground here. Norton's current now you can clearly see is I2 minus I4, right? And then now it's simple. I2 here is simply equal to GM2 VID by 2 minus VID by 2. I1 here is GM1 VID by 2. The same current flows here. The same set of arguments now. So I1 is GM1 VID by 2. This I1 flows through a resistance of 1 by GM3. So it sets up a voltage here. And therefore causes the same current to flow here. I4 is also same here. Okay. So I4 turns out to be same here. VGS1. Basically all the transistors are identical. And therefore this current turns out to be exactly same as this current here. And Norton's current IN will be nothing but I2 minus I4. And you get Norton's current, which is GM1 times VID. Okay. So for Norton's current calculation, you can assume it to be ground, but note the coupling which is there between these two. And that's why you are saying, suppose I had each transistor separately biased. If this little wire had not been there, this point would have been gone to a bias voltage. And this point would have become ground. This point would have become ground. And then this part of the voltage cannot contribute to this part. What would have happened to then I4? I4 would have been 0. Because note that this part is ground. And this part is ground. So I4 would have been 0. And only you would have gotten 0.5 GMVID by 2. So you can see that this little connection that is here is causing a doubling of the Norton's current. Otherwise, you would have obtained simply 0.5 GM1 VID here. And so Norton's current is getting doubled because of that. So that's the major advantage that you get here, because voltage gain will be nothing but Norton's current multiplied by Norton's resistance here. So you're getting a doubling of the current because of this mirror action here, which wouldn't have happened if you had simply biased it. Okay. All right. So let me finish with Norton's resistance and then we'll be done with this today's lecture here. So, all right. So Vx and Ix here. All right. So we are doing this calculation. We want to calculate what is Ix. Okay. So Ix, I'm saying is some part will flow down, some part is coming from here, I4, and Ix is equal to I2 minus I4. Okay. I2 minus I4. All right, let's focus on the lower half first. So I4 we'll worry about a little later on. Let's focus on the lower half here. So lower half, Vx is going here, I2 is going down, and we have this transistor here. This is R05 as usual, and this part I've drawn over here. Okay, this is ground, this is gate is ground, and something is connected here. What is connected here is 1 by GM3, right? Resistance here. Okay. So this part is you're looking into the source, and therefore this part, this M1 is nothing but 1 by GM1. Okay. 1 by GM1 is coming in parallel with R05. One can neglect R05. All right. So this I2 that comes here, note that I2 that you see here. How much is this I2? I2 will be equal to Vx, whatever Vx is there. The voltage, so the net voltage between here and ground is Vx. What is the resistance looking down? Resistance looking down will be R02 multiplied by 1 plus GM2 times the resistance here. And what is the resistance here? 1 by GM. 1 by GM. And note that GM2 and GM1 are the same. So what is the net current going down? It is Vx by 2R02. So when you are looking down here, what are you actually seeing? A resistance of 2R02, not R02. You're not seeing R02. Okay, you're seeing a 2R02 here because this node is not ground. This node is actually 1 by GM1. So the net resistance that you see is 2R02. But now something interesting comes in, because what happens is, so we calculate this current I2, which is Vx by 2R02. So this current that you see here, I2 starts here and flows into where? Flows into M1. 1 by GM1 is of what? M1. Right? So it flows into M1. Alright, so let's pursue now this current here. So this current here, I2, we have already calculated what I2 is, right? It starts here, I2 comes here. Obviously, it will not go down. It will go into M1. Goes here. Of course, it turns, comes here. What does it do now? It will eventually flow to the ground, but via a resistor of a magnitude 1 by GM3. Alright, so it flows here. And so as it flows here, it develops a voltage here, I2 by 1 by GM3. Correct? It's the same current I2, note here. I2 flowing and develops a voltage V01, which is 1 by GM3. This V01, where does it go? To the gate of this transistor. Alright? So now we are done with all this part here. Now let's focus on this one here. So come back here. What is the voltage V01? Here. Now, and all this lower half I've already done, I2. So let's focus on the upper half. We have Vx connected here, and we want to know what is I4. How much will be I4 now? Note that I4 will have two contributions. In a transistor, there are two contributions to current. One comes from VGS, and the other contribution comes from R0. So can I write now Ix? Note that I4 equal to minus GM4 V01, because VGS is, note that VGS is positive, but I4, the direction, the way I've written is like this. Note the current flows from drain to source. That's why there's a minus sign here. And minus Vx by R04, again because of the direction of I4. Okay, so this is the net current I4 that is there. Alright. Now note, interestingly, if you multiply GM4 by V01, what will you get? GM4 is same as GM3. You get basically I2, right? So this I2 that you saw here eventually turns back and is coming here in some form, right? Okay, anyway, so I4 is here. Now what you do is I4, we put here I2, GM4 and GM3 will cancel each other. So I will get I2 equal to basically, what happened? I2 is Vx by 2R02, okay? So we get now I4 is minus Vx by 2R02 minus Vx R04. Alright? You see that? I2, this is I2 we put here in this expression, and this is Vx by R04. Alright? So we get this here. So we have an expression for I4, we have an expression for I2, we will have a net expression for Ix. Okay, so let's do that here. So I've written here all the expression here. I2 is Vx by 2R02, I4 is here. Let's put both of them together. So we get Ix equal to Vx by R02 by Vx by R04. That's the net Ix, and Vx by Ix is R02 parallel R04. So we get the same thing. We get exactly the same result, but note that is much more involved. It's not that this is ground. It's not that this is ground. In fact, when you are looking down, you are seeing actually 2R02. But then what happens is the current that flows down, it starts here, comes back here, develops a voltage here and modifies this. So what you are looking up is also not R04. Right? What you are looking up, if you look at it here, is not R04. You get a 2R02 there also. And so this 2R02 here and the 2R02 here in parallel give rise to R02 and an R04 here. Alright, so you end up getting R0, which is R02 parallel R04. So, in fact, in all these differential pairs, more complicated differential pairs, also similar things will be happening. Alright, and the final result that you will be getting is this. So now, what we'll be doing is as follows. You know, in more complicated circuits, this is the real way of calculating output resistance. This is what is happening. But what we would be doing is, we would be saying that this point is ground. And we would be saying that this point is ground, resistance looking down is R02, and resistance looking up is R04, and the net resistance is R02 parallel R04. Because after doing all of that complicated calculation, we come out at the same answer. So why do it then? Even though we know that this is not really correct. This is not really ground. All right. But again and again, repeating it for more complicated differential pairs will become tedious because the final result is going to come out the same here. So please, afterwards, from henceforth, say that this is ground, but remember that this is not ground. All right. Remember, this is not ground. This is only for obtaining the final value. It's a shortcut to obtaining the final value. That this is equal to approximately ground. This is R02. This is R04 here. So let me wind it up. R0 is R02 parallel R04. IN equal to GM in VID here. And the net gain comes out to be GM R02 parallel R04 at this particular point. The gain at this particular point is double the gain of what you would have obtained if this thing had not been there. You would have obtained simply 0.5 GMRD here. So the gain is double. So now you see why this circuit is so important. Biasing is very easy now. I mean, I don't need any bias circuitry. Bias point is stable. Common mode gain has become much smaller. Differential mode gain has become double. You get all the benefits through this particular stage here, and that's why this is one of the most important stages here. Okay. All right. So let's stop here, and then we'll continue.